I can make a trend line. Yay. Now, so the point of what we're trying to do here is to give some idea of how correct this trend line is. So I can have this trend line. I can make it out of any data set that I want to. It can be a data set with points all over the place, like can have some that looks more like that, or I can have the data more grouped, and visually I can kind of tell the difference between the two of these. But in the end, I'm going to have two models, two things that say y equals mx plus b, or if you have a higher order model, some other equation. But at the end of the day, I'm going to have two equations, and I need to have some idea of what uncertainties are associated with that. Like if I get a number out of this, should I expect it to be within like a barrel per day if I'm looking at a production value, or should I be looking at like being within like 1,000 barrels per day of my estimated production value? You might think like if you're trying to forecast the production of a well into the future based on some production history, and you fit a curve to it, like you had to do in the second, like you had to do or are doing in the second part of the homework. You might want to know how off your final answer is going to be, because that's going to be the difference in the amount of money that you're going to expect to make out of this well. So knowing the uncertainties associated with your trend lines is kind of a big deal, and that's what EV and ES are. It's called they start to quantify what those uncertainties are in different ways, right? So ES is the uncertainty with your slope, right? So uncertainty in slope. So that means that I have my expression y equals mx plus b, right? This m is going to be whatever I estimated it to be, plus or minus whatever ES is. ES is the uncertainty in the slope. This means that I'm not plotting ES. It's not going to show up on a graph. It's just an uncertainty in the slope. So if I was going to use this equation, I could say, okay, nominally, my model will spit out whatever I estimate m is going to be times x plus b. But I know that like my upper bound, say, if m is positive, like I could get up to m plus es times x plus b, or I could get a value as low as m minus es x plus b. Does that make sense, everyone? That's kind of the idea behind uncertainty in slope. That value m that you compute might be as high as m plus es or as low as m minus es. You just don't know where it is. All right? Cool. All right, so that's what ES is. Any questions about what slope error is? Yes.
Oh, not slope error, but about error.
Okay, well, we'll talk about that next. Oh, error in general or EV?
Well, it asks for the estimate for error using the confidence interval and then standard error. Isn't that the same?
Not quite. We'll talk about that. All right. So much for her error in slope. Let's talk about the other one. So, got my graph. Y, bunch of points.
Marius,
Yes.
could you focus that in a little bit? It's like It should autofocus once I like get there.
So you keep autofocus, yeah.
It's because his hand is there.
Yeah, sorry. If I get it out there, it might.
Oh, there we go.
Cool.
Oh.
Oh, well, we'll work with that as we can.
That's fine.
Yeah.
Just send it.
All right. All right. Well, we'll try. Anyhow, so we were just talking about how error in the slope. Error in values, or EV, is next. So this is different from standard error. Standard error just talks about, you have your trend line, you have your data, how wrong is your trend line? If you look at the equation for standard error, it's square root of the sum of the squares over n minus 2. So this is this term in the numerator. What this sometimes called is the sum of the squares of the residuals. So if I looked at, like, this would be a y, which this has x and y coordinates, and this would be like something that's at the same x and has the y value of y hat, right? So y minus y hat is that value there. It's how off the trend line is from the data at wherever you have data for. So essentially, you're just looking at your trend line, looking at the data that it was constructed from, and seeing how wrong it is. That's what standard error does. All right. On the other hand, you also have EV. So another line. What EV is trying to measure is how off the, I'm hoping that it kind of just starts to work, is kind of like how we're talking about error in the slope, and how, and that kind of gives you an idea of how off your slope might be. You can kind of find the maximum that you can be wrong, the minimum that you can be wrong based on changes in your slope. What EV kind of measures is how off is every value. So you kind of get an upper band and a lower band of, this is the maximum error in your values. This is the minimum error in your predicted values. So it's like the minimum, so it's like how right or wrong y hat can be. All right? So like, you might think of it as like y hat plus or minus EV. It's your uncertainty in y hat. Okay? All right. Does that make sense to everyone?
Yeah.
Teresa doesn't look like she's convinced.
Does that have anything to do with my question? No, right?
Remind me of the question, because I thought I started with it, so I might not have. What was your question again?
It says like A wants an estimate for error in the determination using 95%.
Oh, right. Okay. So, so the error that I'm talking about is error in the values, right?
Sure.
So that would be this.
So that one's easy.
Yeah.
Okay.
Error in the values opposed to error in the slope, EV and ES, if you want to remember it like that. And that's as opposed to standard error, which
Oh, so one's EV and
eventually, what would you call it? So EV is how wrong each value might be. It's uncertainty of that. This is different than what standard error is, which is not the error in the values in each individual value of the trend line. It's just how different your trend line is from your data.
Okay? Does that answer your question?
I think so.
Okay. Cool. So in order to get the upper and lower confidence bands, how would you do that?
You would want the y hat plus or minus u.
Right. So this line gives you y hat. This line is y hat plus EV. This line is y hat minus EV.
And then that, your trend line is the one, that's your original data.
Yeah.
There's,
Your original prediction, yeah.
so like in our
The
case,
prediction, called the trend line that you computed.
Yeah, so it'd be like, for this one, it'd be like flow rate by the
that would be,
delta P times, like by the X we.
Yes.
Yeah.
Yeah.
Through a
Yep.
alright.
Darcy's law. No, it's not. You find delta P, then you use Darcy's law. Do
Yeah, it's called. There are several different ways to do it. So you just might have done it a different way. However, when you plot your line back on, so when you plot your trend line, it should look like it fits the original data set. If it doesn't, you did something wrong. All right. So that's EV and ES. Any questions there? Cool. All right, so that's that. All right, so critical T value. What about critical T value?
Is it any other value than just one from the table? Like, is there another critical T value? Just,
Nope.
okay,
There-
I thought there was a formula.
There is a formula for the T value for your data, but that T value is not the critical T value.
So you never use that T value. You always use the critical.
So when you're
Wait, which one's the critical? Table one?
yeah. So if I'm computing, say, I remember the formula for EV. So it's something like that square root 1 plus 1 over n plus n y hat minus, x hat minus x bar squared over n sum x squared plus n sum x quantity squared. Is that true?
Yeah,
Yeah, that's true.
Okay,
Yeah.
cool. So this is describing uncertainty in the values of your trend line, right?
The only thing there's, in the last dimension on the right, there's no n.
All right.
Is what I have down.
I forgot out of hand, but the exact formula doesn't quite matter right now. So I'm not going to worry about it too much. So when I get a value out of this, it gives me kind of the error in my trend line, right? The uncertainty in the values of my trend line. Is that true?
True.
Okay. So we can't. So statistically speaking, we can kind of think of things outside of those confidence bands, outside of the value plus of that, outside of that y hat plus or minus EV area as being outliers. Would that make intuitive sense?
Okay, yeah. Outside those
Yes.
two things are okay.
Let's say. So,
Okay, outside. Yeah.
like on this, if I had a point that was like up there, it's like, okay, maybe I don't quite trust those values. Or if I try to apply this model and I actually start to record things that are up there that should have been down here, then okay, maybe this model is doing something weird. All right. Those are out. Those are kind of. It's called. We can kind of maybe think of those as outliers. Okay. So when we I'm gonna say this. So when we compute a so when we compute a t-value, we're kind of looking at our data and seeing if it and seeing if there's a correlation between these two data sets, right? That was like the point of making the t-value and comparing that. I'm going to get back to outliers. So when you do that comparison, you pick the confidence interval that we do, which is normally 95%, bless you.
Thank you.
When you look at the 95% confidence interval, what you can kind of think of that as analogous to is when you look at like a bell curve and you go 2 standard deviations from the mean and say, okay, all of my data is, 95% of my data is in this in this interval. So when you're comparing, your data set's t-value versus the critical t-value, you can kind of say, okay, I can be confident like 95% of my data, that 95% of my results that I'm going to model here are going to be in this interval. Does that make sense? So like, I have my trend. So I have my trend line in here, and I know that this isn't going to be perfect. I call it because it's a statistical model. It's not. Nothing perfectly follows this model, but I can be certain. But I can have some confidence that 95% of all observations are going to fall inside of these confidence bands. Okay, it's kind of the same. It's kind of the same idea. The same way that we call things outliers that are outside of it, and we think of them as outliers if they're outside of these bands, and say, well, the same this because we picked a 95% confidence interval, 95% of all of our observations should follow this trend within these bounds. Okay, cool. So, because of so that kind of guides what t-value we want to pick here. So if we picked the t-value that we computed for our data set, that's called all that t-value, the t-value for our data set, all that does is it answers the question of whether or not the data set meets the 95% confidence interval, whether or not it meets that requirement of saying this, which called this data will. The data that I have is going to reflect 95% of any observation that I get. Which means that this value might be really, really, really stinking high relative to what the critical t-value is. The critical t-value is just kind of like, this is the lowest that t-value can be and still kind of meet that criterion. So when we're looking at what our error can be, which t-value do we want to use? Right, we want to use, this is the lowest bar that you have to jump over in order to be in the 95% confidence interval. So we want this t-value to be our critical t-value, because that's the lowest that the t-value can be and still meet our requirements.
So that's the one you got on the table you used to.
Correct. Yeah.
And do we have to calculate the t-value for a data set?
The thing I do ask whether or not your data set's valid or something like that, which is, in short, saying, does the t-value for the data set meet this criteria? Because if it doesn't, we have crappy data.
Okay, I say by you see. Okay.
Yeah. All right. Any other questions about that? All right. I'll try to be clear about that in the future. All right. And so that, we've talked about plotting the confidence bands. So I think that's everything, yes.
Okay, so can you go over finding K, because I'm not getting units canceled.
Okay. So, you mean kappa? Okay. So you got something like that?
Uh-huh.
Cool. All right. So when you make your equation, you get something like that.
Right.
And if you have to call it, and depending on how you set things up for your x, say your x is delta p, your m is all that jazz, b is this, y is that. So units of a are what?
Centimeter squared.
Okay, I'll just do a length squared. L, length. Units of dynamic viscosity,
PA second.
PA seconds. And that is the same thing as like a, what, force per length squared times time? Okay. So let's, and we're trying to get to what units?
Unit list.
No.
Oh, wait, that's why, because centimeter squared, I'm getting the units per centimeter squared, that can be, okay, never mind.
Which is the units of Darcy's.
Yeah, okay.
Cool, you're all set then. All right, yes.
When did we have to find kappa in this?
Yeah, the point was to find the permeability of the sample that all this data is from.
Oh, really?
I don't know what the overlap question is.
Yeah, so once you got slope, you gotta back out a value for
Oh, just by
permeability.
relating the equation of y equals mx plus b to, okay.
You got it.
Oh,
That's not that bad.
It's really not.
I was expecting that we were gonna have to.
Nope.
No, no.
But the appropriate units for permeability, like Teresa's saying, are not meters squared. It's Darcy. So
So you have
you should sure to convert. I listed the conversion on the bottom of the sheet. So should have
That's
it.
it.
Cool. Any other questions? And this, barring the fact that I might screw up in finding where I saved this video file, it should be on YouTube within like a couple hours after class. But and do you have any other questions? Yes. It'll be on a private YouTube channel. So you'll be famous to everyone who's in ENGR 3, who was in ENGR 315 and this class. And this class.
Yeah, he's gonna put the link in.
I'll make sure they have access to it. Any other questions? All right. Well, the time is yours, or Yin's guys, as they say.
Yeah.